In our last lecture, we were looking at some practical application of two more industrial chemicals, and we had looked quite extensively at the number 2 industrial chemical, which was nitrogen. Indicated that nitrogen was obtained for commercial use by fractional distillation of liquid air, liquefying air, and then allowing the temperature to come back up, and when the temperature reaches minus 196 Celsius degrees, the nitrogen comes off as a gas, leaving behind the rest of the air, which is primarily oxygen, as a liquid. Some of the major uses that we talked about were providing an inert atmosphere for food storage, used for quick freezing, if we want to fast freeze foods to keep their flavor and their texture, using liquid nitrogen. Also in the dairy industry or agriculture industry for quick freezing and storing animal semen for artificial insemination. Production of ammonia, which is the number 1 use of nitrogen, which is to produce ammonia, which is further used then to produce fertilizers like ammonium nitrate. The production of ammonia, just in a simplified and unbalanced form, is that the nitrogen that is obtained from the air is reacted with hydrogen, of course, to give us the NH3, and then it is carried on through other chemical processes. So we had taken a look at that aspect, or that particular industrial chemical, and just quickly then this morning I want to mention number 3 industrial chemical, which again surprisingly is very readily available because it's oxygen, which is the other approximate 20% of the atmosphere. So when we liquefy air, we let the nitrogen boil off, and what we have left then is the liquid oxygen and a few other liquid gaseous materials. Notice the boiling point of oxygen is minus 183. So we have to get it to a slightly higher temperature, 13 degrees higher, before it boils. So we can separate nitrogen from oxygen by fractional distillation. 3 major uses, and the biggest one is the first one. The steel-making industry uses a lot of oxygen in the blast furnaces, where we're trying to then remove the oxygen and sulfur from the iron ores in the smelting process, and we do that by blowing heated oxygen through carbon, which makes carbon monoxide, which reacts with the ores and then finally releases the metal. We'll talk a little bit more about this particular process in the chapter on oxidation reduction reactions, but for the time being we'll just mention that this is one of the major uses of this gaseous element that we have, oxygen. Breathing support, of course, in a hospital, in medicinal use, if we have somebody who has a lung that has failed or has respiratory problems, emphysema, pneumonia, and we want to have them breathing less or being able to provide sufficient oxygen for the body to function, then obviously if we replace the air with an oxygen mask, we can give the person 100% oxygen versus 20% oxygen that they would breathe in normally, meaning they only need to take in 1/5 as much, 1/5 the volume of gas to give the body the same amount of oxygen. So the person can breathe more slowly, can breathe less deeply, so it can be used in those cases where we have injuries or breathing problems. One of the others is in sewage treatment, not directly, well, yes, directly as the oxygen, but also as its allotropic form, which is ozone. We've talked about allotropes before, so ozone is an allotropic form of oxygen. O2 and O3 are both then allotropes. The oxygen is used in sewage treatment because as sewage comes in, we need to have microorganisms that will eat up, chew up, then the fats, the oils, the proteins that come in, the starches, and we use then various types of yeast to do that. And the growth rate of these microorganisms is dependent upon the amount of dissolved oxygen. And so if we blow oxygen through the sewage, it means that those microorganisms can react much more quickly and therefore break down the material in the sewage much quicker. And so air, if you ever visited a sewage treatment plant, you'll see these large beds with air bubblers coming through, and actually they're moving through oxygen, not just air, to speed up this sewage breakdown. Also now, ozone is being used as a final treatment of the wastewater before it's released back to streams and lakes. The normal is to use chlorine, but one of the problems, and we've mentioned this problem before of chlorine, one of the problems of chlorine as it moves into the environment or makes chlorinated compounds in the environment is that they last a long time. They sit around as toxic compounds for a long time. And so if we use chlorine as the final treatment, that's to kill bacteria, etc., before the water is released. So the final treatment in a tertiary, a three-step sewage treatment system, is to treat it with then something that will kill microorganisms, and chlorine has been the common one. Well, as I say, one of the problems are that chlorine compounds that can be produced in sludge and water and mud where the chlorine gets in contact, and thus give us then chlorinated compounds that can be harmful. Well, ozone doesn't have that problem. Ozone, once it bubbles through, reacts and kills the microorganisms. It breaks back down into just regular normal oxygen, so we have no toxic effect. There aren't too many sewage plants in the United States that use ozone at this point, but most of them are beginning to switch over to that process. The Springfield Southwest Sewage Treatment Plant was one of the first in the nation to use an ozonator as the final process of treating the water before it goes back into the streams. It's very effective, and when the ozone breaks down, it goes back to oxygen. The oxygen that's given off can be trapped by covers and recirculated back and reconverted back into ozone once again. So we have a built-in cyclic system, and also in the process do not put a chlorine compound or halogen compound into the environment. So increased amount of oxygen being used in that process. All right, well, that wraps up what I wanted to say about Chapter 9 then, and so this morning we'll begin looking at Chapter 10. Chapter 9 dealt with the phase of matter that we call the gas. Molecules are far apart. We said they don't interact with each other. If they collide, they just bounce off. No interaction again. A lot of space between them. So that's the gaseous phase. Now, in Chapter 10, we're going to look at the two more condensed phases of matter. We're going to look at liquids and solids. Now we're going to put the particles close enough that, in fact, they do interact with each other. As a matter of fact, many of the properties of liquids and solids are dependent upon these interparticle interactions. So we'll start first of all by looking at liquids and looking at what are the things, what are the forces then that exist between these molecules. Now, when we talk about liquids, we'll always be talking about molecules. I'm not talking about solution now, I'm talking about a liquid, which means that we're talking about a pure substance. All liquids are molecular, all right? Solutions aren't. We know that solutions can be molecular or they can be ionic, etc. But when we talk about liquids per se, we're talking about molecules. So we're saying, what are these forces that exist between molecules in the liquid state? Well, we can categorize them into two major categories with a couple of subcategories. The first or strongest of the intermolecular forces is called hydrogen bonding. We'll take a look at this in just a minute. Then there are a group of slightly weaker forces that are put together in a term called van der Waals forces. And within van der Waals forces, there are two, again, subcategories. One which is called a dipole-dipole force, and one which is called a London or dispersion force. Now, the physical properties of liquids, such things as vapor pressure, boiling point, viscosity, surface tension, these are things we'll be looking at as we go on. But all of these properties, these physical properties, depend upon the strength, the magnitude of these intermolecular forces. So when we look at a liquid, when we look at the molecules of a liquid, we need to be able to determine which of these forces exist. And that allows us then to predict something about these physical properties. All right? So let's take a look then at each of these now independently and talk just a little bit about how they arise. Let's first of all look at the strongest of the intermolecular forces, which is the hydrogen bonding. Now, hydrogen bonding is a pretty select bonding force. There aren't a lot of molecules that have it because it requires that hydrogen is there, and further it requires that the hydrogen is bonded to a highly electronegative element. And the three highest electronegative elements that we have are nitrogen, oxygen, and fluorine. If we went back to Chapter 7 on chemical bonding and looked at the electronegativity table, we find those are the three that are the highest: nitrogen, oxygen, and fluorine. So hydrogen bonding primarily occurs in compounds which have then a nitrogen, oxygen, or a fluorine in it with a hydrogen directly attached to that oxygen or nitrogen or fluorine. Those are the only group, or the major group, that will have hydrogen bonding. And the reason I'm hedging a little bit, because there is a small amount of hydrogen bonding that does occur along with sulfur compounds. And actually in our final chapter, when we talk about biochemistry, we'll talk a little bit about hydrogen bonding that does involve then sulfur also. But for the majority of our discussion, we can focus on these three. Now let's see how hydrogen bonding occurs. Let's go ahead first of all here and take water. Water has hydrogen bonding in it. You know, we spent some time in determining how we went about doing Lewis structures and predicting geometric shapes. We didn't just do that because that was lots of fun. We did it because we can use it now to make some predictions. First of all, then, if I talk about water, H2O, and we can do just a general structural formula like that. Hydrogen is directly bonded to oxygen, therefore we would predict that hydrogen bonding should exist. Now, water, based on Lewis structure and electron pair repulsion, valence shell electron pair repulsion, tells us that water is a bent molecule that looks something like this. And we finish the Lewis structure, we have a couple of electrons, non-bonding electrons on the nitrogen. So even the non-bonding electrons were important in doing our Lewis structures. So that's water. Now, the pair of electrons that are shared by oxygen and hydrogen, oxygen is so much more electronegative than hydrogen. And we talked about this before, polar bonds, unequal sharing. Well, the electronegativity of oxygen is 3.5 and hydrogen 2.1, and therefore those electrons are pulled very strongly to the oxygen. Well, that essentially means that this hydrogen sitting out here now becomes almost electron empty. It has almost lost its electrons. Remember, ionic bonding occurs when electronegativity difference is 1.6 or greater. We're at an electronegativity difference of 1.4, so we're getting pretty close to this thing being an ion. So this hydrogen is almost electron empty. In other words, that s orbital that's sitting there, its valence orbital on the hydrogen, has almost no electrons in it at all. Well, if we had another water molecule now that happened to be located right here, like such, and this pair of electrons here. Now, because of the proximity of this pair of electrons with an empty s orbital on the hydrogen, we actually will get some bonding, some sharing of that other pair of electrons. That hydrogen now that we see right here is sharing this pair of electrons as well as the pair that it actually had to form its own covalent bond. This is the hydrogen bond. The hydrogen bond is actually a weak coordinate covalent bond. If you recall, we said coordinate covalent meant that one species provides the pair of electrons to form the bond instead of two single electrons. Coordinate covalent bond. So this is the hydrogen bond that exists in the water molecule. And any molecule that we can draw that has then non-bonding electrons on a highly electronegative element along with hydrogen attached to it, we can get hydrogen bonding occurring. So it could be in a molecule like an alcohol. We could have C-C-C-O-H. It would still have its bent shape, still has a pair of electrons. And even though these hydrogens aren't involved in hydrogen bonding, because electronegativity isn't that much different, this hydrogen, which could be now on another of these alcohols here, I'll just write C3 up here, this hydrogen then could form now a hydrogen bond with this oxygen on that alcohol molecule. So we would have hydrogen bonding existing. And as I indicated, this is the strongest of the intermolecular forces that exist. If we have hydrogen bonding, it is the predominant force in the liquid. So we need to look for those particular elements and then look at the structure to see if in fact the hydrogen is attached to the oxygen. It doesn't mean that automatically something with oxygen and hydrogen in it is hydrogen bonded. For instance, we could have this molecule, which would have the chemical formula CH2O, and it looks like, well, we've got the oxygen that we wanted, and we've got a hydrogen in there. We might suspect it has hydrogen bonding. But notice that the hydrogens here are not bonded to the oxygen. The hydrogens are bonded to a carbon. This molecule would not have hydrogen bonding, whereas the alcohol would have, or water would have, or ammonia. If we look at ammonia here, I have just enough room to do one more. Ammonia has this, well, it's actually pyramidal. I didn't draw that with dashes, but it has a pair of electrons here. And if another ammonia were to come along above here or below, we'll just put it over here. If we had a nitrogen now come up like this with, and then this pair of electrons on this nitrogen, again, could be shared by this hydrogen, which has become partially electron deficient. And so therefore we could have hydrogen bonding in the ammonia. And the more hydrogen bonding we have, the stronger the intermolecular forces. The first one under the grouping called van der Waals forces was the dipole-dipole. And this comes about any time that we have a permanent polar molecule. Oops. So if we have a permanently polar molecule, we have then dipole-dipole interaction. Again, we did this in Chapter 7. We not only did the geometric shape, but we also predicted whether or not a molecule was polar. We talked about the vector sum of the electronegativity differences. Well, for instance, water is a polar molecule. And what I'm going to do here is I'm just going to draw water like this. And so we'll put one side positive and the other negative. Actually, we showed from a vector standpoint, looking at the water itself here, we said that there was a vector acting this way and this way, a net vector acting this, so the oxygen side was partially negative and the hydrogen side partially positive. So all I've done here is just kind of circled this like this and made this the molecule. Now, if it has a permanent plus and minus end, that plus and minus end is going to be attracted to the plus and minus end of another water molecule. And each water molecule is acting like a small magnet, being attracted to the other small magnets in that liquid. And so these dipole-dipole forces then are fairly strong. Not as strong as hydrogen bonding, which is really more of a covalent, but a fairly strong electrostatic type attraction between the molecules. Electrostatic because of opposite charges. Another water molecule might be oriented this way. We don't mean to imply that all of them are going to line up in exactly straight rows, because even in liquid state, molecules are in constant motion. They're moving around continuously. They're not restricted. They're not moving as fast as in the gas, but they're moving in the liquid state. All right? So the dipole-dipole force. So to predict whether we have a dipole-dipole force, then we need to know, is the molecule polar or nonpolar. If it's nonpolar, it can't have a dipole-dipole force. So if it's a polar molecule, this is going to be then one of the contributing forces within that liquid. The last of the forces mentioned, and the weakest, but the force that exists in all matter, all liquids, actually all matter is a correct statement, are the London or dispersion forces. Both terms are used. So you might see it called dispersion force, you might see it referred to as London force. These forces depend upon two factors, the molar mass or molecular weight, and London forces are directly related. In other words, the bigger the mass of the molecule, the more the strength of the London force. And also molecular compactness. I don't even know if that's a word, but molecular compactness is inversely related. In other words, if we have a molecule which is kind of tightly shaped, it's not going to interact as strongly as a molecule that is spread out, a long molecule, with both having the same mass. And we'll take a look at a couple of examples here. All right? Now, sometimes we also refer to this as induced dipole-dipole interaction. In a molecule, we have a lot of electrons. And if, for instance, we started out and we had the electrons all sort of evenly scattered throughout, we have the plus nucleus, and the electrons scattered out about equal, then there wouldn't be any charge separation in that molecule or atom. But if, for instance, at one instant, the majority of the electrons happen to have shifted, again, we'll put this center here, more of them had shifted to this side, and a few had left over here. For this brief instant, we would now have a partially negative and a partially positive side. that means that it's going to influence, it's going to induce electron shift in the next molecule. And the next molecule over here, the electrons on this side, then would be repelled, so there would be fewer over here, and more of them would end up over here again, and so we'd end up with a little partially plus here and a partially negative, and so we have a dipole-dipole force. But in this case, it's not a permanent polar molecule. It's not because of electronegativity difference, it's merely because of electron movement within the molecule itself. And it's only there for a brief instant and then it disappears. And so yes, we have it for a second, the next second it's not there between those two molecules. So it's an on-again, off-again type of force. It continually comes and goes. It's not permanent, and so therefore it's much weaker than the permanent polarity that we saw in dipole-dipole forces. Now, what I'm talking about when I say that the London force is directly related to molar mass, obviously, the larger the mass, the more electrons we have. And the more electrons we have, the easier it is to actually cause them to be displaced, to shift one way or the other slightly, and give us a weak polar situation. So the bigger the molecule, and in general when we talk the bigger the molecule, we're talking about the greater the mass of the molecule, then the easier it is to disturb, to shift those electrons and end up with a slightly polar, an induced polar molecule. Now, molecular compactness, we said, was inversely related. Let me show what I mean by that here. Let's suppose that we look at the molecule C5H12. Now, there are a couple of ways that we can draw C5H12. It's going to have the same mass. These are called isomers, remember? Structural isomers. We can put the 5 carbons in a row, and we could put on the 12 hydrogens. And I'll just use dashes here again to represent the hydrogens. That's one of the structural formulas that we can have for C5H12. Now, I can also do it this way. I could put one in the center, put the 4 carbons attached to the center one, give each of the corner carbons now 3 hydrogens, so it's still C5H12. Both have exactly the same molar mass, 2 isomers of each other, but they will have different intermolecular forces. This molecule, being more compact, it's kind of bunched together, its electrons cannot shift as readily as this molecule, which is more spread out, a linear molecule. And so if we were comparing these two, this one would have stronger London force. This would have weaker London force relative to those two. So the more compact the molecule, the weaker the London forces become. So when we look at then chemical to try to determine something about these physical properties we're going to be looking at for liquids, again, vapor pressure, boiling point, viscosity, surface tension, when we want to predict then those particular physical properties, we'll need to take a look at what forces exist. So let's take a look at a few examples here of predicting then what forces do exist or when they exist. And the first question we have to look at here says, which have dipole-dipole forces? Now, to determine which has dipole-dipole forces, we have to know which of these are permanently polar molecules, meaning we have to do a Lewis structure. So if we're going to then determine which is a polar molecule, the first thing we'll have to do is draw the molecule itself. Well, the first one The I2 is pretty straightforward. The only way we can hook two iodines together is in a straight line. And obviously, two iodines are going to share the pair of electrons exactly equal, and so there's no polar bond. If there's no polar bond, we can't have a polar molecule. So this is nonpolar. If it's nonpolar, it can't have a dipole-dipole force. Well, what about CCl4, carbon tetrachloride, common name, and we did talk about that once before, carbon tetrachloride. If we draw the Lewis structure, we're going to end up with a tetrahedral molecule. Once again, looks something like that. And if we add up the vector forces, even though there's an electronegativity difference, chlorine is 3.0, carbon 2.5, so there's a small vector of 0.5 that way, but there's also one this way, and one out this way, and one this way. And we said that if we had four like attached groups on a tetrahedral type structure, they're going to cancel each other out, no matter which way the vectors are going. So this is, in fact, then, a nonpolar molecule. It's nonpolar not because it doesn't have polar bonds. It does have polar bonds. But it's nonpolar because of its geometric shape. Remember, we said that polarity was the vector sum of electronegativity differences. All right, so that's a nonpolar molecule. Therefore, it cannot have dipole-dipole forces. Well, what about H2S? If we do the Lewis structure for H2S, we're going to end up with this is the geometric shape, a bent molecule, because we have two non-bonding pair. So basically, the electrons are located tetrahedrally, but two of those are non-bonding pair, so when we throw this one away and this one away, we're going to end up with a molecule that is just a bent or angular molecule, sulfur and the two hydrogens. And are there polar bonds is the next question. Well, yes, sulfur is 2.8, I believe, and hydrogen 2.1. So we do have a vector that direction and that direction. And so, yes, in fact, we're going to have a vector. So it is a polar molecule, and therefore it will have dipole-dipole forces. So we know that this molecule is going to more strongly attract other H2S molecules than either of these two are. And if these two both don't contain, then the difference of their attraction would depend upon basically their mass. And so if we looked at the mass of the two, that would give us some predictive property of the strength of the dispersion forces, because that's all they would have, dispersion forces. This one's pretty simple. It says, which have hydrogen bonds? Well, again, however, we do need to look at the Lewis structure from the standpoint of knowing which things are hooked to which. But quite obviously, the first one does not have hydrogen bonds. And why do I say quite obviously? There's no hydrogen. Very good. Can't have hydrogen bond if we don't have hydrogen in it. Now, the rest of them have hydrogen in, so they're all possible then could have hydrogen bonding. If we look at the first one here, what we have is we have a molecule that looks like this. Oxygen bonded to oxygen, bonded to hydrogen, and a hydrogen. And this is what our overall Lewis structure would look like. This is actually even the predicted shape. All right. Should that have hydrogen bonding in it? Yes. It has the two necessary ingredients. It has hydrogen attached to a highly electronegative element, oxygen. So yes, this will have hydrogen bonding in it. Now, the next one, pH3, if we did its structure, it would be pyramidal pair of electrons there. It has at least the general appearance that it has some non-bonding electrons that are necessary for hydrogen bonding. But the thing is, in this particular case, the hydrogen is not attached to one of those three highly electronegative elements. As a matter of fact, the electronegativity for phosphorus is 2.1 and hydrogen 2.1. It's not even a polar molecule because they're nonpolar bonds. Okay? So, no, this one does not have hydrogen bonds. And finally, this one I don't think we even need to draw out. The hydrogens would obviously have to be attached to carbon, and carbon is not one of those three we said, and therefore it does not. And so the only one that has hydrogen bonds in those four is the H2O2, called hydrogen peroxide is the chemical. Any questions on any step that I did there? Now, in the next question that we're going to look at, we're going to ask the question, which is the major intermolecular force? Keeping in mind, the strongest is hydrogen bonding. So if the molecule can have hydrogen bonding, that will be the strongest. Then dipole, and finally London forces. Everything has London forces, but that's the weakest. All right. Well, if we glance across here, let's look at this one. What can you tell me about that one? What's one of the forces we would predict there? Can have hydrogen bonding, and if it has hydrogen bonding, we don't need to go any further. That's the strongest bonding force that it can have. Well, that can't have hydrogen bonding, doesn't even have any hydrogen in it. That, we just said, doesn't have hydrogen bonding. That can't have hydrogen bonding. That can't have hydrogen bonding. But if we look over here, this one could have hydrogen bonding. Notice this nitrogen, hydrogen. As a matter of fact, we'll just write it this way. This is an amine. Remember our organic group, R-N. In this case, we have two hydrogens attached and a pair of electrons. Hydrogen attached to one of the three highly electronegative elements, and so therefore, yes, this has hydrogen bonding, and so the primary force here is hydrogen bonding then. So that's our primary force in those two. Now, once we've decided that we've covered all the hydrogen bonding, the next thing we're going to have to look at is, do we have any dipole forces? Do we have any permanent polar molecules? All right. Well, let's take a look. Carbon monoxide. We hook it together. All right. So do our Lewis structure. We've got a couple of pairs of electrons and a pair here. Actually, in this particular molecule, carbon ends up electron deficient in carbon monoxide, and that's one of the reasons carbon monoxide is such a reactive chemical. Carbon monoxide doesn't tend to exist very long. It tends to react with oxygen in the air and become carbon dioxide very quickly. But if we have it in a confined place, then of course it can be a problem. But what about this? 3.5, 2.5, we do have a vector, so therefore this end is negative and this end is positive. It is a polar molecule, and if it is a polar molecule, that means that its primary is going to be dipole force. Its primary is dipole because it didn't have any hydrogen bonding. The next strongest was the dipole. We look at this one here, PH3. We just drew this a moment ago. That is a pyramidal shaped molecule. And again, if you question about how you go about this, you can always refer back to chapter 7, where we did a lot on drawing structures, Lewis structures and geometry, geometric shape. And we still have a pair of electrons here. But 2.1 and 2.1 are the electronegativities. And even though the geometric shape would give us a possible polar molecule, the fact that we have non-polar bonds means that it's not a polar molecule, so it does not have dipole-dipole force. So the only thing left for it to have is the London force, or the dispersion force as we've also called it. So that's its primary attractive force, are these induced dipole or London forces. So we've taken care of that one. What about CS2? Well, CS2 looks like this. Looks like carbon dioxide, CO2. It's a linear molecule. We do have a vector because sulfur's 2.8 and carbon's 2.5. So we would have a vector like that of 0.3. But we also have a vector over here of 0.3. And so what would the net vector be for that molecule? 0. And so therefore it's a nonpolar molecule. And so it cannot have dipole-dipole forces. And so again, the only force that it could have would be the London force. And finally, Br2, which will be a bromine attached to a bromine. Obviously, it's a nonpolar molecule because anytime we attach two like atoms, they're going to share electrons equally. So it's nonpolar, and so therefore the only force that it could have would be London force also. So once again, then, just looking at the overall group up here, we had 2 with hydrogen bonding. We had 1 with dipole-dipole, and these 3 all here were all London force as the primary force between the particles. All right, any questions on that idea? Now, as I said, one of the places that we apply these principles then is in predicting certain physical properties. Let's suppose that we were to set up a system that looks something like this. We're starting over here. We take a closed container that has a pressure gauge on it, and we place some liquid in the container. And initially, then, when we look at the gauge, there is no pressure. But after some time, we come back and we take a look, and in fact, we're reading a pressure. 1 whatever unit it is. 1 torr, 1 atmosphere, 1 pounds per square inch. It doesn't make any difference, but it's reading a pressure, which means that there are now gaseous molecules. And where did the gaseous molecules come from? Well, they came from molecules in the liquid that were able to escape into the gaseous phase. And we have a certain pressure that would finally reach, and it would remain that. And if we looked at the pressure in the container over time, what we'd find is we start, of course, with 0 pressure down here. This is the pressure. This is just a time factor. And as we go along, we would see pressure build up until finally it would reach a constant value. Now, when it's reached this constant value, the question is, does that mean that molecules have stopped escaping from the liquid? As a matter of fact, we call this escaping process, we call that evaporation. And so the question is, has evaporation stopped when we get out here? Is that why the pressure has become a constant? And the answer is no. Evaporation hasn't stopped. But we have 2 processes occurring. Once some of the molecules have escaped from the liquid into the gas, we have these molecules now running around up here. If one of these molecules collides with the surface, it might actually lose some of its kinetic energy. Again, we're back to this idea of kinetic or energy of motion. It might lose some of its kinetic energy to the rest of the liquid molecules and become retrapped as a liquid. But when it lost its energy, something else in the liquid gained some of that energy and now could possibly escape. Well, the reverse process is called condensation. And when evaporation becomes equal to condensation, we're right here. We're at that solid line. When evaporation equals condensation, that's the rate, I should say. The rate of evaporation equals the rate of condensation. We're going to have a constant line in pressure. And we refer to that pressure then. We could extrapolate this over to our edge here. We refer to that pressure when these two become equal as the equilibrium vapor pressure. Equilibrium vapor pressure. Equilibrium because two dynamic processes are occurring. We have evaporation but condensation, and they're occurring at equal rates, so the number of gaseous molecules becomes a constant. And if the gaseous molecules, remember we're now back to thinking about gases in Chapter 9, if the number of molecules becomes a constant, then pressure should become a constant, provided one other variable that we have to keep a constant, and that would be the temperature. Because obviously kinetic energy of the liquid is affected by temperature. And if kinetic energy of the liquid is affected by temperature, then equilibrium vapor pressure is also going to be affected by temperature. So if we take a look at the vapor pressure of a particular liquid now, versus temperature, we will get something that looks like this. We see that as temperature increases, the vapor pressure of the liquid increases. Now, it is not linearly related. In other words, it doesn't just continue on in a nice straight line like this, but notice that it's curved or exponential in its relationship. This is called an exponential rather than a linear relationship. But vapor pressure is directly proportional then to temperature. Okay? Vapor pressure is directly proportional to temperature. So if we increase the temperature of the liquid, we're going to increase its kinetic energy. We're going to increase the number of molecules that it can escape from the liquid. We're going to increase the vapor pressure. Now, again, as I was saying, that to determine the vapor pressure of a particular substance, to make some predictions, then we're going to wonder, how strongly do the liquid molecules attract each other? If things attract each other very strongly in the liquid state, it means it's difficult for them to leave in the gaseous state. And that means that they're going to have a low vapor pressure at a particular temperature. If the molecules have very weak intermolecular forces, have only then London or dispersion forces, the molecules can escape much easier, and therefore we're going to have a higher vapor pressure. And in our next lecture then, we're going to take a look at some examples of chemicals using these three forces that we've talked about today, then to make some general predictions of vapor pressure and go on and talk about other properties of liquids. In Chapter 9, we've talked about pressure, atmospheric pressure, and of course we don't think a whole lot about the fact that we live in this sea of air that is exerting a pressure on us. For instance, the normal pressure is about 14.5 pounds per square inch on our body's surface. If you dive into a swimming pool, of course, you notice the change in the pressure of your eardrums, etc., from the increased pressure due to the water. Let's suppose that we were an alien and we had just come down to Earth, and we forgot about the fact that the atmospheric pressure on our planet was about 1/10 that of which it is on the Earth's surface. And we opened up the doors to our spaceship and went to step outside. We might wonder what would happen. entering an atmosphere that is 10 times as great as the atmosphere that their body would be used to. But we'll take a look at what the atmosphere pressure really can do. What I have set up here is just a can, and I've put some water in it, and I'm heating it to boiling. Because water vapor is more dense than the air, it tends to fill the can with water vapor, and we see water vapor now coming out. And I'm going to then cap it and take the heat away. Once I do that, of course, the water that is in the liquid or the gaseous state inside will begin to reliquefy, meaning that the pressure inside of the container will decrease because the number of gaseous molecules in there will be decreasing. So I'll go ahead and take away the flame, and we'll cap this up. And it begins cooling down, and you can already hear the fact that as it begins to cool down now, the sides seem to be caving in because we're decreasing the pressure inside. I'll go ahead now and start to pour some ice water over the top of this, and we'll see what effect it has on it as the ice water now begins to affect the can. Unfortunately, the best side of the can collapsing is over here, so let me turn this around. But you can see what has happened to the can. We didn't do anything other than the fact that we've decreased the pressure inside of the container. So again, the alien that would step out into an atmosphere 10 times greater than what they were used to would receive this type of crushing effect on their body. If you were to dive down to, say, a depth of 1,000 feet in the ocean, your body would tend to be collapsed or crushed because of the pressure. Even a submarine can collapse under that type of pressure condition. And so the reverse, of course, is true as we leave the Earth's surface and go to a decreased pressure. Our body, which is set to function at this 14.5 pounds per square inch, does not function too well when we get to outer space, where we would only have 1/10 of a pound per square inch, or even at a point where there would be a vacuum. So the reason that the space people, the astronauts, etc., have to use a space suit is the space suit is providing them with an artificial atmosphere duplicating what we typically have here on Earth. If not, we end up with problems of gases coming out of the blood, breathing problems, and many, many other problems that could occur. So we see that, in fact, 14.5 pounds per square inch that we swim around in this atmosphere on Earth really is a fairly great pressure when we take a look at it overall.